Our project is on secure inter-FPGA communication. So we have used two boards. One is for the encryption and the other one is for the decryption. So for the encryption part, this is the top module of the encryption. In this, we have used the AES encryption part. So here we have not used the complete AES encryption. We have taken the inspiration of the AES encryption part and to run it on the FPGA board like in a less number of rounds. So we have modified the AES encryption and we have instantiated in the top module, and we have used the VIO and ILA to get the outputs here. So the other one is the so this is the code for the top module of the encryption part. So this code is given to the FPGA board of the first one, which is used for the encryption. So in this the key and the plain text will be sent, and we'll get the output as the ciphertext. So the next part is the decryption part. So this is the top module of the decryption part, and we have used the same model as which we have used in the encryption one to decrypt the code, and we have used the VIO and ILA here to get the plain text back. So the code will be sent on to this second FPGA board, so in which the decryption works. When we send the same key which we have used in the encryption part, then we'll get the and we'll give the input of the ciphertext, and we'll get the output as the plain text which we have given in the board A, that is which we have used for the encryption. So that's it.
This Verilog code is written for the modified AES encryption, which contains 4 rounds, in which every round follows the same process as they are running in the loop. We give inputs as clock, reset, start, round key, in block, and outputs as out block ready. Start tells the module to begin processing, and in block is the input plain text, and out block is the output ciphertext. Ready goes high when the input is valid. Next comes the function sbox, that is substitution box, which is one of the core components of AES encryption. It introduces non-linearity into the cipher. The sbox logic is written here in the code. Next is the reset condition. This part runs when the reset equal to 0. This resets every value to 0. Now coming to the start condition, when start goes high, it performs add round key, which sets running equal to 1 to begin round processing. Now AES round processing loop runs, which extracts each byte from the state and applies the sbox function to that byte, and also writes the transformed byte to new state. In our design, the AES style lightweight cipher follows a structured round base architecture for both encryption and decryption. In the encryption process, each round performs 4 major transformations sequentially. The first step, subbytes, applies a nonlinear substitution to every byte using an sbox, which ensures confusion in the data. The second step, shift rows, cyclically shifts the rows of the internal state matrix to provide interbyte diffusion. This is followed by mix columns, where each column is mathematically transformed using finite field multiplication, further spreading the influence of each input bit across the state. Finally, we apply add round key, where the round key is XORed with the state, providing key dependent scrambling of data. In decryption, the operations are reversed in a precise mirrored sequence. The round begins with add round key, since XOR is its own inverse. Then inverse mix columns is used to mathematically reverse the column mixing, followed by inverse shift rows, which undoes the row shifts. The last step, inverse subbytes, applies the inverse sbox to reverse the substitution. These inverse operations ensure that the original plain text is perfectly reconstructed when the same key is used. This symmetrical but inverse structure gives AES-based designs strong security while still being hardware friendly for FPGA implementation.
A demo for the encryption module. So first we have given an arbitrary key and an arbitrary plain text, and we have set the reset to 1. So right now nothing is supposed to happen. So we will first set the reset to 0 and we will give a small start pulse. So as we can see now, there is a ciphertext which is generated from the encryption module. We are going to look at the decryption module. Due to multiple hardware managers not being allowed to be open in the same PC, we have first disconnected the encryption module and copied the ciphertext, and we have placed the same ciphertext here and the same key which we have provided for encryption. And right now the reset is 1, so nothing is supposed to happen. So first we will set the reset to 0 and we will send a small pulse, and as we can see, the plain text which we have got here as the output matches with the plain text which we have given initially, and this completes the encryption and decryption.